In this video, we're going to talk about what are called characteristic functions. So characteristic functions. And we're also going to talk about, these are related to what are called Heaviside functions. Heaviside is the last name of a mathematician who used these functions regularly. So what we're going to do, before we actually formally even define what these are, I want to find the Laplace transform just by using the definition. I want to find the Laplace transform of the function f, where f is going to be a piecewise function that's going to be 1 if, say, t is between 3 and, let's say, 10, and 0 otherwise. There's nothing special about 3 and 10, by the way. This works for any values a and b. Again, since we're talking about the Laplace transform, I'm going to assume that those a and b are positive. But, all right, so let's get to work. So this Laplace transform is going to be the integral from 0 to infinity, e to the negative st, times f of t dt. And you can think of this as the integral from 0 to 3, plus the integral from 3 to 10, plus the integral from 10 to infinity. Okay, so plus the integral from 10 to infinity. So just breaking it up that way. And the integral from 0 to 3 and the integral from 10 to infinity are going to be 0 because our function f is 0 at on those intervals. So this integral is going to be 0, and this integral is going to be 0. And what we really need to do is to compute this middle integral from 3 to 10. So this is going to be the integral from 3 to 10, e to the negative st. Between 3 and 10, f of t is going to be 1. So this is 1 dt. Okay. And now what we're going to do is just integrate. We are anti-differentiating with respect to t. So that means that we're going to divide by negative 1 over s. We have e to the negative st. We're going to evaluate this from 3 to 10. And so let's factor out the negative 1 over s. And if t is equal to 10, we got e to the negative 10s minus e to the negative 3s. And there's our Laplace transform. To write this a little bit better, I'm going to write this as e to the, let's see, this will be 1 over s. I'm just going to distribute the negative through, so this is going to be 1 over s, e to the negative 3s, minus 1 over s, e to the negative 10s. Okay. And this function is what's called a characteristic function. This characteristic function is, so characteristic functions are functions where what we have is, really these are defined over any set, but we're going to define them specifically over an interval. We use chi, the Greek letter chi, for characteristic. This is defined as the function that's going to be 1 if t is between a and b, and 0 otherwise. Okay, so this is formally what's called a characteristic function. The reason why these are useful and the reason why these come up a lot, and actually the reason why they come up in the context of our course, is that if I were to integrate some function, say f of t times the characteristic function, think about what's going to happen. Right? If this characteristic function is 0 outside the interval from a to b, this is just going to turn this into a nice finite integral of f from a to b. Okay, so that's how the characteristic function gets used, and that's why it is so useful. So that's again called the characteristic function. So in general, I think it's worth just writing this down. The Laplace transform of the characteristic function over the interval from a to b is going to be 1 over s e to the negative as minus 1 over s e to the negative bs. Okay, so just replacing our 3 and 10 with a and b in general, that's what we get. So this is another value on our table that we have. All right. There are also what are called Heaviside functions. So the Heaviside function is a kind of characteristic function. It's a certain type. And the Heaviside function is going to be denoted u of t. And what it is it's going to be 1 if t is greater than or equal to 0, and 0 otherwise. So it's 1 if t is greater than or equal to 0, and 0 otherwise. So you can think of u as the characteristic function from 0 to infinity. Okay, nothing mysterious yet. The next step, though, is to talk about the shifted Heaviside function. So the shifted Heaviside function. And what we're going to do is the same thing that we did with the Dirac delta. We're going to shift it by a. So the shifted Heaviside function, we're going to denote u sub a. So u sub a of t. And this is going to be 1 if t is greater than or equal to a, and 0 otherwise. Again, for the sake of our course, we're always going to assume that a is positive. If a is negative, then this function is just always going to be 1, and integrating anything by 1 doesn't change anything. It's not very interesting. But what we're going to do is let's think about the Laplace transform of this Heaviside function. So let's calculate just by hand. So let's calculate the Laplace transform of the shifted Heaviside function, and that's going to be the integral from 0 to infinity, e to the negative st, u sub a of t dt. And this is going to be 1 if t is greater than or equal to a, and it'll be 0 otherwise. And so what we're going to do is this turns out to be the integral from a to infinity, e to the negative st, times u of a is 1 over this range, dt. And now if we evaluate this integral, we're going to have negative 1 over s, e to the negative st, from a to infinity. And we can bring out the negative 1 over s. As t goes to infinity, this is going to be 0. And as t goes to a, this is going to be e to the negative as. And altogether, what we end up with is positive 1 over s, e to the negative as. So this is the Laplace transform of the shifted Heaviside function. Okay, a few other things just to say about these functions. If you were to take the Laplace transform of the shifted Heaviside function times some function of the form t minus a, I want to think about what would happen here. You would have, by definition, the integral from 0 to infinity, e to the negative st times whatever our function is, which is u sub a of t, f of t minus a dt. And so what's going to happen is you can do the trick that we did above. Just by definition of u sub a, this is going to be 0 unless t is greater than or equal to a. And if t is greater than or equal to a, this is 1. So this is going to be the integral from a to infinity of e to the negative st, f of t minus a. From here we can substitute u is t minus a. That makes du dt. And let's think about our bounds. If t goes from a to infinity, then u is going to go from 0 to infinity. And let's see, t is going to be u plus a. So this is e to the negative s, u plus a, f of u du. Inside the parentheses here, just to zoom in real quick, this is a sloppy looking u. There we go. So e to the negative s times the quantity u plus a. And now let's think about what's going to happen. I can factor out this e to the negative sa from this exponential term. I can bring the e to the negative sa outside. And I'm left with the integral from 0 to infinity e to the negative su f of u du, which is nothing more than the Fourier transform of our function little f, which we write as capital F. Okay, and so that's how this is going to work. So therefore, just to write this out, we're almost done with all of the values on our table. This is, we just showed that the Laplace transform of u sub a of t, f of t minus a. That's e to the negative sa times the Laplace transform of f. Okay, so multiplying, what this says is that multiplying a function by the shifted Heaviside function has the effect of multiplying the Fourier transform by e to the negative as. Okay, that's the rule. That's how this works.